Question number 3 that says the bottom of a vessel is inclined at an angle theta and a hemispherical dent of radius r as shown in the figure. This is the figure. If a liquid of density rho is filled in the vessel to a height h above the highest point of the dent, find a suitable expression for magnitude of force of the liquid pressure on the dent excluding contribution of the atmospheric pressure. So I have redrawn this picture over here. This is the spherical dent, hemispherical dent, and this is the liquid, and this highest point has a height depth h from the free surface, right? Now this is an equilibrium, and this inclined plane makes theta angle from the horizontal direction, right? Now if we imagine that this dent, which is basically surface, if this in place of this, let's say there was a complete this inclined surface as a bottom, and the same liquid was placed in this dent. If the same liquid is present at this dent, then also you'll find this entire system will remain in equilibrium as it is, right? So if we are interested in measuring the pressure force on this surface, we can also replace this dent by the same fluid occupying this space. In that situation, you'll find the forces acting on that liquid portion is going to be a pressure force from at this bottom, which is going to be like a normal reaction, we can call it, and it's gravitational force, which is going to act vertically downward, and there will be third force coming because of the pressure. Now all these three forces must be balancing each other. That means they all three will be in equilibrium. So we can say the force of the liquid will be basically resultant of these two, which is N plus mg. Now this N is the pressure force on the base of the hemisphere. Now since this vertical height, this max point has depth h and this radius is r, so this total height of the center of this or total depth of the center of hemispherical dent from the surface is going to be h plus r. So we can write the pressure at this base of the center of this base and the base area. Now you'll find this pressure is going to be like rho gs, the total height, if we exclude the atmospheric pressure, and the area is going to be pi r square. This is also have been written in short, otherwise we need to go for integration, but we know that this varies linearly with the height. So as we go upside, height decreases, as we go downside, height increases, so we can take the average value. After doing integration, you will get the same expression. So it's like pi r square rho g in within bracket h plus r. This is the pressure force on this liquid we have assumed over here from the bottom. Now how much the gravitational force is going to be? So you say the volume into density into gravity. Volume is 2 by 3 pi r cube g and rho. That's total mg. Now these are the two vectors. Resultant's magnitude we are interested in. So resultant magnitude goes like under root f1 square plus f2 square plus 2f1 f2 cos the angle between the two vectors. Now we are interested to find the angle between these two vectors, so this bigger angle is going to be there. If you draw a vertical line over here, you'll find this angle is going to be theta. So the angle between n and mg is going to be 180 minus theta. So that's cos 180 minus theta, which is basically minus cos theta. So it's will be like n square plus mg whole square minus 2 times n into mg. Now we can substitute the n value as well as mg expression. So it turned out to be a Hughes expression. That means n square, which is basically rho g within bracket h plus r into pi r square whole square plus mg whole square, which is 2 by 3 pi r cube rho g whole square minus 2 times these two numbers product into cos theta, because cos 180 minus theta was cos theta, right? Minus cos theta, so there is a minus and there is a cos theta, and whole raised to power 1 by 2. So that big expression is the expression for magnitude of force of liquid pressure on the dent, and we have found it using the or replacing this dent by a liquid having same density, in fact the same liquid. Okay, so that's our answer. Thank you.